Thank you very much. Good afternoon. Indeed, I'm here for the third part of this lecture. The first part we talked about thinking machines and singularity. In the second part, we talked about artificial intelligence. Today, I'll be talking about expert systems and machine learning. How machines learn. What do you mean by machine learning? Who knows what an expert system is? Who has heard of that? Okay, well, expert systems have been around since the 60s. It's not new. It's very old. And it used to be a big part of artificial intelligence. Many people today don't consider artificial intelligence anymore. So an expert system is a computer system that tries to emulate the decision-making ability of an expert, a human expert. And it tries to do that by reasoning, using some knowledge, so it reasons about knowledge to solve some given problems, and using some contextual facts, or facts about that problem. Why did people build these expert systems? And they have been used in many, many fields, medicine in particular, but in many other fields, financial analysis, engineering, design, manufacturing, planning, and so forth. Why did people build these expert systems to emulate humans? It's not really just for fun. There was a good reason for that. One of the main reasons is that some of the problems the experts were working on were not just local, they were in many places, and we had very few experts. We couldn't distribute these experts, the human experts. So to replicate that expertise, such artificial experts were needed. Also, in many cases, we had an expert that was about to retire. And when that expert retires, we lose the knowledge. So how do we copy that knowledge and we can either use it for training new experts or actually use it as an expert, an artificial expert? So the question was how to preserve and duplicate this expertise, the expert knowledge, and put it in a machine. And that's why, from the 60s, people started working on that. So what's the difference between programs that are considered expert systems and normal programs? Well, normal programs in computer science, you tell a computer step by step what to do in a programming language. So there is a language to express the different steps that a computer has to follow. Expert systems don't use that paradigm. They're completely different because we don't know the problem that we will have to solve. We just have some knowledge. We have different facts each time about the problem, and the problem can be completely different that we have to solve. Yet we have to write one program for it. So these programs, called expert systems, use what I just mentioned, some knowledge. So there are two kinds of knowledge. There's the expert knowledge that represents what the expert knows. So this is typically coded in terms of rules. If you have this condition and this condition and so forth, then you should do this. So there's a conjunction or disjunction. You may have negation. So there's a way of expressing some conditions with logic, and then you have a consequence, a conclusion, and that conclusion would be the creation of a new fact or maybe leading to a conclusion, the conclusion of the problem, so solving this complex problem that we're trying to solve. There's another kind of knowledge which represents the context. These are what we call facts, the facts about the problem. Okay. So this is how it looks at a very high level. You have the knowledge base, that is what represents basically the expertise, the knowledge of the human expert. Through intensive interviews, we extract that knowledge from the expert and we code it in terms of rules here. Then you have an inference engine that will reason using this knowledge base and some other facts that describe the problem. Okay? So here's an example of a rule that is expressed inside the knowledge base. Okay, so this is in the case of mycin. I'll mention mycin later on. This is related to medicine and germs and biology, things like that. So how does it work? So basically, you have some facts about the problem. You have a problem. You have a question. The problem is typically a question, and you have facts about that problem. Giving those facts, we will look inside the knowledge base, well, actually the inference engine, we'll look inside the knowledge base, are there premises of some rules that match the facts that I have now in my fact base, okay? And then I will find many rules that may apply. We call them, they may fire, okay? So they may apply. Some are certain, some are uncertain. There's some degrees of certainty that are attached to these rules. And then there's a process of selecting which rule to apply. We apply that rule, and the conclusion of that rule will become a new fact. So the fact base will increase as we are applying the rules until the conclusion to the problem, so the solution to the problem becomes one of the facts of the fact base. If we fail to do so, then we say the problem is not solvable, otherwise we solve the problem. Okay, so that's how it works. And this started in the 60s, as I mentioned. The famous ones are dendral, you have mycin, then metadendral. So they created an expert system that can be generic. You can, transform it into many other fields. Yeah, E-mycin in 79. And by the 80s, it became a huge business. So expert systems were very ubiquitous in many fields, and it was estimated that the market for expert systems reached $1 billion. This is in the 80s, so it was huge. And thanks to the success of expert systems, people had new faith in AI, because at one point people lost faith in AI. Now, thanks to expert systems, it came back, and more government agencies were funding research in AI because there was potential profit out of it. There are many problems with, this is just a list of examples where expert systems are used in medicine, and I will not read that. I'll let you read the examples. There are problems building expert systems. It's not that trivial. The biggest problem is getting that knowledge out of the head of that human expert. How to create the appropriate interview to get the right knowledge. Why is it that difficult? Because often we don't know what we actually know. So when you ask the question to the expert, they think they told you everything, but actually there are other things that they take for granted that are things that are important, but they take for granted they don't tell you. It's only in front of a new case they will tell you, oh yeah, you have to do this, but you didn't tell me. Oh yeah, well, I forgot. Okay. So getting that knowledge out of the expert and coded in a knowledge base is extremely difficult. There was also, you don't necessarily use just one human expert. Often you use many human experts. Well, even if you use the same human expert, after a while you realize that the rules that you create from that knowledge that you extracted from these experts, you may find contradictions. They tell you something in the morning and they tell you something else in the afternoon. They didn't lie to you, but because different rules apply in different ways depending of the circumstances, and they don't tell you all the details. Okay, so you end up coding it in a way that is not necessarily true for all cases. There are also many missing rules, and because of these missing rules, you can't solve all the problems. Another problem is the inconsistencies between experts. They may not all agree how to solve some problems. Okay. So these are major issues. And one of the reasons that expert systems were part of AI, the main reason is that this inference engine that uses logic was often coded using programming languages that were specifically designed for AI, among them Prolog and Lisp. So these are languages that were designed for AI programs, and they were exploited to build these inference engines. And people who are saying, well, it's not AI anymore, it's because, well, this knowledge base is handcrafted. You have to extract it from the experts, and then you have to handcraft it. It's not the machine that learns this knowledge. Well, the machine does the inference and solves the problems, but all this knowledge is built manually. So now I want to go to machine learning. And the thing is that some people claim that this knowledge can be learned by the machine automatically looking at cases. So you show the cases to the machine and let the machine learn by itself. So there is indeed a potential there, and some people are working on it. But in order to build that knowledge automatically with the machine, you have to be able to present all the possible cases that a human expert has seen during their career, which is extremely difficult. You don't necessarily have all that data. So what is machine learning? Have you heard that term before outside this class? Any idea what it may mean? What is machine learning? Yeah?
I'm just going to assume it's like the ability for any man-made, well, I mean, all machines are man-made, but it's the ability for a machine to learn from like continuous tests, I suppose, for their ability to create their own mindset.
The ability to learn and the ability to create their own
mindset.
Mindset.
So they develop a personal way of thinking, I suppose.
Sure. Even though we don't know what thinking means.
Yeah.
Yeah, sure. Okay, no, it's a good attempt. So machine learning is actually a discipline within computer science, and it's heavily overlapping with artificial intelligence. Actually, it's subsumed by AI. And this discipline is concerned with designing algorithms, so programs that will allow this machine, this computer, to change its behavior. So learning, as you try to describe it there, is actually changing the behavior of the machine. So the machine doesn't have one behavior. I coded one thing, that's it, and that's all it knows what to do. But it will learn how to change its behavior based on new data that I'll give it. Okay. For me, machine learning provides means to learn from large data, interpret the trends in that data, and then adapt to that data. And adaptation is the key here. Because that's opposed to these static programs. I write a program to do something, and the computer will do it again and again and again and again without getting bored. That's what computers are good for. But in machine learning, it's not just doing the static thing. It dynamically changes. It learns to adapt to the environment. So this is what I wrote in red here: learn from experience so that I can adapt to my environment. For the machine, the environment is the data that it's getting from the different sensors or what I'm sending it. And the experience is basically the data that it looked at. Okay, that's the experience. Just to give you an idea, so that to better understand what I mean by adapting and learning experience and all that stuff, let's make the analogy with, well, compare programs, sophisticated programs that we use today, and other sophisticated programs that I claim have machine learning in them. So if I look at an accounting program, that's a very complex program where you have all these accounts and the rules of what goes where and why and how to improve things, and that doesn't have any machine learning whatsoever. It could, but normally it doesn't. Basically, it has sets of rules that are hard-coded in the machine, and it'll tell you when you make a mistake and things like that. Okay. Querying a database. You can have an extremely large database. You go to a department store, they sell hundreds of thousands of things, and you go to the cash machine and you buy something, it's scanned instantaneously, the price is printed on the screen. It has no machine learning. There's a query that is hard-coded in the code of the machine, and it knows how to go and use the index to find the product immediately in display. You can have way more sophisticated queries to know, for example, how many products of this type were sold between this time, in this store, and this store, and that store, whatever. So you can create many complicated queries, but they're hard-coded in the program. You can run it again and again, and it'll give you the same answer again and again. Well, let's take some robots. Robots are intelligent. Well, if I go to a manufacturing plant where we, let's say, build cars, you have robots, okay, that go and put some pressure and weld different pieces together, assemble pieces. Well, you will program in the program of that robot the exact X, Y, and Z coordinates and the exact pressure, the exact temperature to put, and it'll do it again and again. It's not adapting. If you change the model from this car to another car, you'll go in the program and change the coordinates, and you change the pressure and the temperature, and it'll do it again, a different movement. There's no adaptation whatsoever. It's a robot, but it's not intelligent. So here are examples of programs that require machine learning. If I want to build a medical image analysis program, I cannot program in it all the possible cases. For example, if I'm trying to identify where cancer is in a mammography, in a mammogram, I cannot program all the possibilities. It's impossible. Okay? So I have to show some examples to the machine and let it learn by itself to recognize where's cancer, where's no cancer. Okay? And I'll get to that later on. Filtering data for analysis. So I have data coming in, and some of the data is interesting to me, some of the data is not interesting to me. I can write filters that are static. But if I change my behavior, I have to change my filters. I can write a program that adapts to me. My interest changes in that data, so the program will watch me and learn from my behavior, and then will filter automatically the data that is interesting to me and what is not interesting. Now let's go back to the robots. If I'm sending a robot to Mars, I don't know how the environment is there. I don't know if it's sandy, you have rocks, you have hills, I don't know. I haven't been there. How can I program the path that robot has to take? I cannot. So I will teach it on Earth different cases, and I will allow it to learn to adapt to those different environments. And then I release it on Mars, and if it finds a rock in front of it, it'll see if it can climb over it or go around it. Okay? I will not decide for it. The machine will decide on its own. So it adapts to that environment. So it's learning. And you can see that the program for that robot to do the assembly of different parts of a car is completely different from the program of the other robot that is trying to discover something on Mars. Okay? So the example that I often give to illustrate how the machine would learn is the following. So this is a metaphor. Imagine you have a child that comes here in this classroom, and I have a set of buckets. The buckets have colors, and I have a pile of balls, different sizes, different colors, different weights, different structures, whatever. They're all balls. And I ask the child, watch me, what I'm doing, and learn. And I say nothing else. And then I grab a ball, I look at it, so I'm doing my assessment, I'm looking at it, and then I decide, without saying anything, to put it in one of the buckets. take another ball, look at it, put it in another bucket. After a while, the child will realize that what matters to me is the color. So I'm putting the blue ball in the blue bucket and the green ball in the green bucket and so forth. The weight didn't matter, the size didn't matter, the structure didn't matter. It's only with observation that they can realize that. After a while, I can tell the child, okay, it's your turn. I give the ball to the child, and the child will say, okay, I'll put it here. Okay? That's exactly what the computer would do. So the computer is doing what the child was doing. The child was observing these training examples. I'm training that child. And noticing that the color mattered, the other features didn't matter, and build a model in his or her head, and then was able to execute afterwards. Okay? So the question is how to write a program such that that computer would now build the model and use it afterwards to adapt. Adapting, in this case, the child will adapt because I gave him a new ball and I didn't tell him which bucket it should go to, and that child used the model to adapt to that situation and will put it in the right bucket. Okay? So, in general, what we have in machine learning, we have what we call training data, data that has been labeled. So in the case of the balls and the buckets, the label is the bucket. I showed the child where I put that ball. Okay. So now the program will go over this training data and learn from it a model. The model will say, what are the features that discriminate between this class or that class and that class? The classes are the buckets in this case. Okay? Then, so that model, I'm representing it as a cloud. It can be different things. It can be rules. It can be a formula. It can be many different things. There are many ways of creating that. Let's make it more friendly. I'll put a happy face there. Now I have new data that hasn't been labeled before. So this is the ball that I gave to the child and say, now it's your turn. Put it in its right place. Okay. So I will use that model that I learned and label the new objects that I haven't seen before. Okay. So the computer builds that cloud and then uses it, what I call the model, and uses it later to adapt to new situations. Okay. I'll give you examples so that you will see what are these colors and what are these squares, okay, in different applications. So this is still research, ongoing research. We have many ways of doing this. There are many other challenges. Challenges are, for example, determining what are the relevant features. Remember that ball? The child realized that the color mattered. The weight, the structure, the size of the ball were irrelevant. So every single object that I want to classify, I have to express some features out of that and see which features are relevant in that task. And that's not trivial, depending upon the different applications. Then we have to come up with an algorithm that is efficient and effective. So efficient, I want to be able to go through that and learn, not in 100 years, I want to learn in a few seconds. Okay? So how to optimize these algorithms and how to make them effective in the sense that they don't make too many mistakes afterwards. We will make mistakes. The child may make mistakes and put some balls in the wrong places because the color wasn't seen before or different reasons. Okay. Also, there are many challenges related to the model itself. How do I represent that knowledge that I learned from the data? How do I represent it? And then, how do I effectively use that model in order to label the objects, the new objects that haven't been seen before? All these are trivial in some cases and very complex in other applications. So here are examples of applications where the computer can learn. You all know what spam is. You all bombarded with spam, and you don't want to see it at all. And yet people continue to find ways to get to your mailbox. So there are rules that you can add to your application that you're using to read your email, saying, if the email contains this word, I don't want to see it. Or if this email comes from this person or that person, I don't want to see it. Okay? So you can create static rules that are called filters, so that the spam filter will eliminate some of the bad messages that you don't want to see. The spammers, they're humans. They adapt. They adapt to your filters, and they find other ways to pass through. So what you want a computer that rather than following strict rules, a computer that adapts to you. Because what you consider spam, somebody else may not consider spam, and vice versa. So many applications now exist where the email player that you have will look at your behavior. What did you throw and what did you read? Okay, and from that, it will build a model. The training is looking at what you do, and will build a model that represents that knowledge. What is for you spam and what is not spam? What is important, what is not important? So the computer is adapting to you. Another example is credit card approval. You go to the bank and you ask for a loan. They look at your age, your income, whether you're married, you're not married, what is your education, all that stuff, whether you had a loan before. These are the features. And based on that, they will decide whether to give you the loan or not. Are you solvable or not solvable? Will you return that loan with interest, yes or no, or you will go bankrupt? Well, they have now programs that look at all the data in the past, and they learn from that experience. Not just the experience of one agent, but all the agents of the whole bank. Okay? And then it will recommend to the agent, it will see, oh, yeah, you can give this guy the loan, and they will give you the loan. Or say, warning, this guy may not pay back on time. Then the agent will use that to make the decision. Okay. Another example is when you use your credit card. There is an authorization request that is sent from the merchant to the credit card company. And the authorization comes back after they check whether the transaction that you're trying to do, what you're trying to buy, for example, fits your behavior, your past behavior, where the purchase is happening, the amount, the kind of thing you're buying, and that happens very rapidly. And then comes back and says, yes, it's okay, or no, this seems not good. Don't authorize it. Okay, they're using machine learning because every single person is different, and you cannot hard code it. It has to adapt to the environment. So these are cases that are used today. Okay, machine learning is already there. It's not fiction. So there are many kinds of machine learning. There's supervised, unsupervised. So the supervised is when you give the training, you give it data that has been labeled, and you say this is the green bucket, this is the blue bucket, the red bucket, and so forth. You label it, and then you have new things that are now labeled afterwards. The unsupervised, there is no training whatsoever. So you provide these, so the balls here, I'm representing them without color, colorless. And you may know how many classes you have, how many buckets you have, or sometimes you don't even know how many classes you will have. Okay. So in general, the way it works, you have some data that has been labeled. You split it into two parts. One part you keep it for training, and you build your model based on that. And then the other part that you kept aside, you have the labels, but you hide them, and then you provide them to this model and see what is the accuracy that that model has. If the accuracy is acceptable for the application, then you can release that model and use it. If the accuracy is not good enough, then you continue to train using a different model, different paradigm, or different data set, and so forth, until your accuracy is acceptable. And of course, the accuracy depends upon the application. So if my application is about turning on and off a power plant, my accuracy has to be very high because the risks are high. I may have a Chernobyl, and then you can imagine the consequences. Or if I have a false positive and I turn off the power plant, well, I have a problem on the grid, the power grid, and also to restart that power plant afterwards will cost me a lot of money, okay, and I have to deal with that. So my accuracy has to be very high. The accuracy for the spam detector doesn't have to be 99.999%. Even if it's at 70%, it's still acceptable. Well, and I may lose some emails and I may get some spam in my folder, but it's not dramatic as having a power plant explode. So this paradigm, well, there are many approaches to solve this. There's what we call neural networks, k-nearest neighbors, decision tree induction, Bayesian classifiers, associative classifiers, support vector machines, and so forth. I'm naming a few here. And the thing is, there's no one winner. Depending upon the application, a different approach would work better. That's why they all coexist. I'm not going to go through all these, of course, but I'll give you an example, well, two examples, k-nearest neighbors and decision trees, because you will understand how the machine actually is building that model. So the first one, k-nearest neighbors, is a very simple one. It's actually what we call lazy learning. The machine is lazy. It will not actually build anything very sophisticated. How does it work? Basically, when you train it, you give it the data that has been labeled. The only thing it does, it just sorts them in one way. Using, for example, a similarity measure to put those that are similar to each other close together. That's all it does. Then when you have something that you want to classify, it will go back to that data that you provided before and say, what is the closest to it? And then when it finds it, it says, well, I'll use the label of that nearest neighbor. And that's the label that I'll give to this new object. Okay? So if I go back to the example of the balls and the buckets, I provide the association balls and buckets. I'll sort them all. Then when I get a new ball, I'll say, what is the closest ball to this one? Okay, here it is. Which bucket did you put it in? You put it there. So this one, I'll also put it in that bucket. Okay? So here's how I represent it graphically. I have this data that has been labeled. I have two classes, gray and green. Then I have this new object that hasn't been labeled before. That's why I'm showing it in red. I have a distance function that compares this one to all these elements that I have here, and the one that is the closest to it, now this one is green, I'll say, well, this red one should be green as well. Okay? Now I can make it a little bit more sophisticated. Rather than have nearest neighbor, I can take the k nearest neighbors, a set of neighbors. So when I have a new object here, I'll take few of the closest, so the closest, the k closest, whatever k is, 5, 10, whatever, and then I'll have a vote among them. And the vote will tell me what label I should give to that new object, okay, new case. The other approach is what we call decision tree induction. And typically doctors understand very well decision trees because that's how they actually work. So this was presented for the first time in a paper in 1983. The idea was presented using this data set, so I'm using exactly the same data set. This data set is just showing different weather conditions and whether the person will play tennis or not. Okay, so these are past observations. The outlook, the temperature, humidity, and whether there was wind or not. And then here the class label, whether the person played tennis or not. And the question is, can I build a model, learn the behavior of this person, and then, given some weather conditions, predict whether this person will play tennis or not? So how can I build that model that represents that information? Well, a model can be represented in a tree like this. I check up the outlook here. If it's sunny, then I'll have to check if it's humid or not. If it's high humidity, then he will not play tennis. If it's normal humidity, he will play tennis. If the outlook wasn't sunny, but it's overcast, you'll see that all the cases that have overcast, the player will play tennis. Otherwise, if the outlook is rain, I'll have to check if it's windy. So you have this decision tree in the leaf nodes of the tree. The tree is upside down. The root is typically on the top, and the leaves are on the bottom. So the leaf nodes will tell you what class it is. The interesting thing is that on this data set, I can build many different decision trees. It's not the only decision tree. Here, I started asking the question, what's the outlook? I could have started with the question, is it windy, yes or no? And create different branches. So the algorithm that this paper was presenting is how to create the optimal, between quotes, tree to represent that knowledge. And it's a recursive process. Basically, you take the data and you split it, start splitting it, splitting it, splitting it, until all the data that is in a set, they all belong to the same class. So each time you want to split it, you have to look at a particular attribute, so a particular feature, and look at all the possible values. So for example, you take outlook. Is it raining? Is it overcast? Was it sunny? Okay, and you create these branches. And then you take it all now the new subset, and you see if they're all in the same class, that's fine. It becomes a leaf node, and I stop. I have the class label. If they're not in the same class, then I have to select another attribute and split it again. Okay. The question is, how do I select an attribute? And the paper talks about a method that uses information theory to look at so the information gain, which attribute actually gives you the best information gain when you separate the classes like that. Okay, so this is just a very high level, 30,000 feet view of two techniques to represent some knowledge. So the first one, the knowledge, is actually just a ranked list. Here, the knowledge is represented as a tree. Okay, there are other techniques that represent the knowledge as a set of rules. Or there could be hyperplanes cutting the space where the data is. There are many different representations of that knowledge. But here I want to give you some examples, because we're talking about the promise of AI. I want to show you some examples of achievements that we have today that you can see around you. You don't realize that actually they're using machine learning. One is the case of autonomous vehicles. I talked about this on Tuesday. We have today cars that drive themselves. And we teach them how to recognize, for example, signs. And then they learn now how to identify these signs by showing you some examples, and then they learn the rest. They know when to turn, when not to turn. So they get all this data coming from different senses, and they adapt to the environment as it changes. So these exist. The problem is not that they don't work well. The problem is that they have to coexist with human drivers who are not very good drivers. That's the biggest problem. That's why they're not on the road yet. But many states in the United States have already approved autonomous vehicles on the roads. Another example is handwriting recognition. When you write the postal code on an envelope and you're sending it somewhere, don't think that there are humans reading all these. There's no way. You have millions and millions of these envelopes being sent. But people have different handwritings. So how do you recognize this as a 9 and not a G, or it's a 6, not a B, or there are different kinds of 6s, different kinds of 3s, and so forth? Well, we teach a program to recognize a 3 from a 5, from a 2. So the numbers are basically those buckets. Okay? And we try to identify those. And the computers are very effective at identifying codes now. It's a little bit more sophisticated than that. Now we have computers that can recognize letters, so cursive writing, as well as mathematical formulae. So when you write on a pad, you write with your handwriting. You can have a terrible handwriting, particularly doctors have terrible handwriting. And the program will adapt to that and change it into normal letters. Okay, that's actually incredibly, it's fascinating actually. Spam filtering, I talked about that. Credit cards, I talked about that. Financial applications. You have thousands and thousands, millions and millions of transactions that are happening all the time. How do you detect where is fraud? How do you detect what is acceptable and not acceptable? You can't imagine humans looking at that all the time. So we have computers that are trained to recognize, so they learn how to recognize what is fraudulent, what is not fraudulent. Recommender systems. So recommender systems to recommend books, to recommend products you buy, to recommend movies you want to watch, to recommend songs you want to listen to. All these recommender systems use machine learning to learn about what you like and what you don't like. Okay, there's also an algorithm called collaborative filtering. It learns from the people like you who like similar things and hate similar things, and then they will recommend to you things that they like that you haven't tested yet, okay, because they're close to your behavior. Adaptive interfaces. So the example I often use is, remember when AI started, people used it as marketing tool. People say, well, my thing has AI, my whatever has AI. People were joking and say, oh, my toaster has AI. With machine learning, same thing. People say, oh, my TV has AI, my toaster has machine learning, my toaster has machine learning, and so forth. But when you say my TV has machine learning, it's not a joke anymore. Some remote controls have machine learning in them. The first one that came up with this machine learning adaptive remote control is Philips. And what Philips did is this remote control that has 4 buttons. You identify yourself. They assume that the average family has 4 members. So you say, I'm number 1, or I'm number 2, or I'm number 3. And then you start flipping through the channels. It learns what you like and what you don't like. So for example, if you go to the first member of the family flips to the sports channels, well, next time it will not go one by one. It'll skip to the sports channel directly. And the number 2 member wants to look at comics, for example, well, it'll learn that automatically. Okay? It'll adapt to that person. Other examples, you all use Facebook, I'm assuming. Many of you use Facebook. Well, Facebook doesn't show you everything. If you have, I hope not, 500 friends, and everyone is posting something, let's say each one is posting like 10 things, you're not going to see 5,000 new posts. There's no way. So the interface will choose what to show you, and it'll choose based on your past behavior, what you liked, what you shared again, what you read, what you commented on. It learns from that model, and then when you have a new posting, it'll decide, oh, should I put it on the screen or should I not? Okay? So there are adaptive interfaces like that use machine learning. I'll go through examples in medicine, and there are many of them, to give you an idea how medicine is also embracing machine learning, big time. So one example I'm working on is helping radiologists going through medical images. So in the case of mammography, humans are not 100% accurate. They make mistakes. Okay, so it's recommended in many countries, they recommend to have 2 readings per mammogram. Because when you have 2 specialists looking at it, the number of errors go down. Unfortunately, we don't have enough radiologists to look at all these images twice. Okay. So one possibility is to have a computer playing the role of the second reader, or maybe even the third reader. Will not replace the human, but at least help that radiologist. One other possibility is actually pre-reading the image before presenting it to the radiologist. Why pre-reading it? Because then you can say, well, here is a region of interest. I learned based on the images that I saw before that that's a region of interest. So the radiologist now will focus on that area and will spend less time on other areas. Okay. So there's a need for that kind of assistance, and that kind of assistance requires machine learning. Another example that my lab is working on, this is the work of Russ Greiner with the Cross Cancer Institute. We want to learn, based on past experience, of course, how brain cancer will develop, will grow. So when there is brain cancer detected, we will bombard it with radiation to treat it. And typically, we don't just radiate just the cancerous cells, we also radiate around it so that we prevent it from growing. That means you kill healthy cells. But why do you have to kill healthy cells all around it? If we know how it will grow, it'll go this way, then we will kill more on that direction and less on the other direction. Okay. And that can be done using machine learning, learning from past cases, and then you can do that prediction. Another example is also in brain cancer. Before you do any surgery, there are many slices that you can take, and then you have of the brain, and then you do the segmentation, a 3D segmentation, to isolate the place that you will bombard. That segmentation takes a long time, so a specialist will do that. It'll take about 20 minutes. Okay. The interesting thing is that different experts may not do exactly the same segmentation, and even the same doctor looking at the same scans in the morning or the afternoon may not produce exactly the same segmentation. So it's a very difficult task to do. So the idea is to learn from previous segmentations and pre-segment it for the doctors. And then the doctor will see it, and rather than segmenting from scratch, they will just adjust the segmentation that has been done by the computer. And rather than spending 20 minutes, they'll spend 5 minutes. Okay, so this is another way of using machine learning, not to replace humans, but to help them in their tasks. Another example, completely different, this is in the case of breast cancer, for example. After treatment, you have an adjuvant treatment, so after you do surgery or chemotherapy, you may want to do some hormone therapy, but that depends upon the different receptors that you have, the different proteins, estrogen receptor or whatever. And there are ways of determining if this patient is ER positive, ER negative, and that it's tedious and it's not necessarily 100% accurate. So another technique is to use microarray data analysis. So this is data that you get after the biopsy. And you get the gene expressions of past patients, and you label them whether they were ER positive or ER negative. And you build a classifier on this. Okay? So this can be done with microarray data analysis or with SNPs, so singular nucleotide polymorphisms. These are the mutations that we have in the genes. And the idea is basically you get this training data. It has been labeled positive, negative, positive, positive, negative, negative, whatever. You learn a classifier. Now you have a new patient coming in, and you will say, based on the gene expressions here, whether this patient is ER positive or negative. And this has a huge impact because if you get it, after you learn, you can determine what kind of adjuvant treatment you can give to this patient afterwards. So it's personalized medicine, basically. Should you give tamoxifen or not, and so forth. So this same idea can be applied in many, many cases. You can also predict whether this person will have a relapse after a certain time. For a kidney transplant, you can predict whether this patient will reject it or will not reject it, or which one will have will strongly reject it, which one will less strongly reject it, and so forth. And then you can use that information to decide to whom to give that organ. Prostate cancer as well, you can predict the toxicity levels, and I'll talk about this in the next slide. Decaxia, to predict whether this patient being treated this way will lose muscle mass, and so forth. So all these techniques for learning can be used in order to help doctors make better decisions vis-a-vis these patients. So it's really personalized medicine. The treatment depends upon the patient himself or herself. So in the case of prostate cancer, when you have cancer, you will, well, there are different possible treatments, but one of them is radiotherapy. You bombard these cells with radiation, and there are side effects. Side effects are measured in terms of toxicity. Toxicity 0 means the patient has no problems. Toxicity 1 is some discomfort, vomiting, bleeding, whatever. It goes up to 5, which is death. The idea is, can I use the same technique to learn from past experience, my other patients, based on their genes and what happened to them when I gave this treatment? Can I use that to learn a model so that when I have a new patient, I look at their genes, and then I can predict what level of toxicity I'll have. If the toxicity will be low, then I'll say, good, I can do this treatment. If I predict the toxicity will be high, I'll say, no, I will not do that treatment. It doesn't help. Okay, it's not improving the conditions. It's not improving the quality of life. So I'll do another treatment, surgery, chemotherapy, or whatever. Okay? So that's the idea. I have now the genes of the new patient, that classifier that I learned before I'll use with this new patient. I will detect whether it's a low toxicity or high toxicity. Okay? So machine learning becomes a tool for the doctors to make better decisions. And that ends my presentation. So if you have questions, please send them my direction.
So the idea of machines coming up with their own way to find the answer that cannot be explained in words, I guess that is perhaps one characteristic of what we're talking about here, but it isn't just words, is it? It's formulas, anything that a human being can use to explain. You could eventually teach a machine to do that. So how much danger is there in the black box potential of the machine somehow knowing things that is unknowable by a human being?
Danger can come from two places. One is those who are programming those machines. Like anything that we build often has two possible usage, the good usage and the bad usage, whether it's nuclear, for example, energy, or anything else. The other danger is when the machine starts doing things that we didn't expect it to do. Some of it could be positive, some of it could be negative. So far, there's no machine that took the initiative on its own to do some things. Any action that a machine took, it's because it was planned somehow in the code. We don't have programs that allow the machine to take initiatives yet. You need, for initiatives, well, not so sure, but to take some initiatives, you have to have some consciousness. We're not there yet. Will there be danger? Yes, because we don't know what that kind of what initiative that machine could take.
I was just wanting to change the topic a bit. I was kind of thinking, in your opinion, if there is a downside in some areas to having these systems. Like, I can't help but think when you gave the example of financial institutions and economic systems, like, it seems to me that if you have an AI or a computer algorithm and system that can accurately detect the level of risk in an investment or something, if you can just go to the computer and know what to invest in, it seems like a lot of how the economy and the stock market works will be lost. Like, do you see instances like that or other areas where the invention of a completely accurate computer system will actually be a downside?
So in the financial market, there's a lot of money at play, and people have tried to play the game using computers. And today, actually, you have computers that are doing the trading for the humans, especially for high-frequency trading. There are many transactions every second the human cannot follow. So you have computers that do that. But the computers, they don't take the decision on their own. There's a program that tells them, here are the conditions, and here what you do. So there are algorithms that do the trading. Those algorithms are not using machine learning yet. Some are trying to use machine learning. The thing is that the people are realizing that machine learning is the best way to do, because as you create these algorithms to do the trading, and many people are doing that, the market is it's a chaotic market. It changes all the time. You try to influence it this way. If everybody uses exactly the same algorithm, of course, it doesn't work anymore. It finds its balance again and again, and you need to adapt. So those algorithms that were written, they don't work anymore because the market changed again and again. So you need machine learning that adapts. Now, your question is, if all these algorithms are using machine learning, do we still need a market, basically? It becomes useless. I think we still need it. And not all programs are the same, like not all traders are the same. And some will win, some others will lose. And some will win more than, and for one to win, some have to lose anyways. And we'll find another balance. The market will adapt to us to the machines as the machines are adapting to the market. That's how I see it.
The internet has noise now. I mean, unpredictable behavior, but it doesn't have intention, as far as we can tell. But you know that there's variation. I mean, every science fiction depiction of what the singularity will look like always starts with this something coming alive. But couldn't it be gradual? I mean, where you would hardly notice that the decisions were being made more and more independently, right? So I mean, I guess that's what they call a soft takeoff. Do you predict, or do you
I think things will change gradually.
Yes, yeah. Soft
and then one
takeoff.
day we'll wake up and realize, ooh, I didn't expect this. So we passed that threshold. And that's why we need to discuss it now, because by the time we will realize, we already passed that threshold. Now, is it coming from the internet or not the internet? I don't think it's the internet per se. The internet is just for me, I see it as the knowledge base, the human knowledge base. Everything is put in there somehow, and it's connected. So
right.
If I know how to use it properly, then I will have all the knowledge I need. Mm-hmm. And the sum of the knowledge of everybody, which is humongous. Actually, today, when you ask any question, the reflex is to go and search it online. Like in the past, we knew how to do mental calculations. As soon as we had the calculators, we use the calculators, we don't have that capacity anymore. We lost it. When we started having these mobile phones that remembered the numbers of my family members and friends, I didn't have to remember them anymore. I just press the button and it calls my friend and whatever. The same thing is happening with the internet. Do I need to know what is the capital of this particular island in Micronesia? No. I will Google it and or use any search engine and I'll find it. So the internet is becoming the collection of all the knowledge. And if you have good programs, good machines that can sift through what is right and what is wrong and what is correct and what is not correct, because there's a lot of garbage on the internet as well, a lot of duplicates, and which one is the correct one, which one is not the correct one, and can exploit it properly, well, just on the side of knowledge, it's way superior to any human.
Right. In Google's purchase of this AI system in the last week, this small company that they purchased for $400 million, part of the
DeepMind.
Yes. Part of the deal is setting up an ethics committee for decisions. What are your thoughts about that? One of the most famous quotes that you've ever made in this course, that I repeat over and over again, is the fact that we could devise a computer that's more ethical than we are.
Yeah.
So is part of the process for that this kind of ethics committee? I mean, it's like going back to my own field, transplantation. In the beginning, it was very ghastly. Transplantation was only offered in very few places. Most people who needed it died. So these committees were literally making life and death decisions. Do you think there will be, ethics committees about, computer plans, like what Google is going to do with the expertise? What do you think that they're...
I am not aware of the role that this committee will have.
Yeah.
I'm convinced that Google purchased DeepMind because of the skills that they have, the people in that company. And actually, we have people from Alberta there, too. I'm proud of that. But so I talked about ethics and machines learning ethics in previous lectures, not this year, but last year. We assume to be, we think we are ethical, but ethics changes with culture, with what we know with the time, because what was ethical here wasn't ethical some years ago, and what was ethical some years ago is not ethical here, and what is ethical here is not necessarily ethical in Africa or somewhere else. Even here, we are influenced by our emotions and other things when we make those kinds of decisions, and I'm convinced that training a machine to know what is ethical, what is not ethical, will be more ethical than humans, that's for sure. So that's being said, I'm not aware what is the goal that Google has with this committee and what is the mandate they give to this committee.
Right.
Yes, we should have committees, if that is your question. We should have committees discussing and deciding about what to do for the future in terms of machines and capabilities of these machines.
So is that enough priming of the pump that there are some other, yay!
So I'm not really sure how far-fetched this question really is, but
Go ahead.
It's about the singularity, and I was thinking, us as humans, we're innately afraid of really powerful things. Us as a society,
we are afraid.
Yeah. Throughout history, we've joined together in dark times to take down people who are vying for too much power. And I was wondering, does the same apply for machines? Because I feel like the assumption is when the singularity does come about, it's going to start with one really powerful machine, and all the little guys are going to follow suit. Do machines have this, I suppose, mentality to ever be afraid of this immense increase in power? Like,
So, first of all, if we are afraid of powerful things, we are only afraid of powerful things if they are against us. If they are in our favor, we are not afraid of at all. We want them. So the same applies to these machines. If these machines are powerful, but they're working for us, and they're working in our favor, we will not be afraid of them. We will welcome them. Come here and help us. If they are against us, yes, we are afraid of them. And most of these science fiction movies show that kind of picture, where the machine will turn against us. And that becomes a disaster, basically. Now, you mentioned the mentality of machines. Machines don't have mentality yet, so do you think machines, I don't understand the last part of your question. Do machines will be afraid also of something more powerful than them or something like that?
yeah, that's sort of the question. Like, would there ever be the possibility of one machine leading the charge into the singularity, but then other inferior machines opposing the singularity? Like, it just seems to me that everyone assumes that when the singularity does come about, machines are going to be like all for it, you know? Is there any possibility that machines would want to remain where they are now?
Well, this is hypothetical because we're not there yet. We don't know how it'll be. But first of all, not all machines have any kind of intelligence. Some of them will reach that level when we get there. So not all of them will be conscious of what is singularity. So I cannot see an army of machines rallying behind one of them that reached this level of intelligence. No. That's number one. Number two, machines are not in isolation. They're connected. So you can see it as one community. I go back to these ants. I'm fascinated by these ants. When you look at one individual ant that doesn't understand this whole architecture, but the whole thing put together is capable of building that. At the same time, is an ant afraid of us? Does it know we exist? Maybe it does. But if it knows that we exist and we're different, is it afraid of us? Well, actually, when we die, the ants will eat us. Part of this, not just the worms. The ants will also have a feast. So I don't think machines will have this kind of mindset, as you said, where they are afraid of more intelligent ones or will rally behind a more intelligent one. I think the most plausible scenario, if a machine reaches the level of intelligence that we have, or superior, it will use those other machines, because it's connected to it, to do other things. So maybe the queen of the ant is intelligent and is exploiting the other ants. I don't know, maybe. But again, this is just speculation about what may happen the day we reach the singularity. I don't know if it answers your question, but
Yeah, like me, I suppose no one can truly know. So I was just getting your input on it.
yeah. For me, I don't see machines in isolation. Machines will be connected. So is it that machine or that machine? It doesn't matter. They're all together. One may be churning and doing calculations, the other one is doing the thinking, the other one is looking at the information, has access to some part of the information, and so forth. It's not just one machine that will be the ruler. I don't see it that way.
As we near the singularity, do you think it will ever be necessary to possibly program feelings in the machine? I mean, Corey's question raises some points like, what if machines can feel, like they feel jealous or they feel afraid of a higher power? Like, do you personally think it will ever be necessary to program feelings into a machine? Because obviously, like, humans are pretty intelligent. Like, the higher intelligence is.
Is it necessary? Yes. Actually, many people are working on this, programming emotions, or at least the expression of emotions. They see it necessary to communicate with humans because we are using emotions when we communicate. When we are sad, when we're happy, when we are angry, when we're surprised. So we express it. And if you want to communicate with machines, machines should be able to express it. Whether they will feel it or not, that's another story. That's on one hand. On the other hand, there's a lot of work also within AI. People are working on machines that can paint, write poetry. That's expression of feelings between quotes. But does the machine feel what it's painting? Not yet. Is it necessary to make it feel so that it's a better painting or better piece of poem? Maybe. I don't know. I think it's useful if you want to communicate with it because our hormones make us feel different things, and we don't have the exact thing as hormones within the machine, but yeah.
So I guess one aspect of this is, what would an artificial hormone be like? I mean, what if you are going to inject that into a machine?
I think you can ask that question to whoever will be talking about nanotechnology. I don't know who's going to talk about nanotechnology
Yes?
This year, but maybe it's a nanorobot that is affecting somehow, like the hormones are affecting us.
Yeah.
So nanorobots affecting the machine? I don't know.
No, well, that's quite relevant. So that's Ross Lockwood next week. So we'll ask him. So our time is up. Thank you very much for an outstanding 3 lectures.